Research and development for tomorrow's weapons. This is the mission of the Naval Ordnance Laboratory. In this task, scientific photography is an important tool of analysis. Its techniques are the product of more than 90 years of development. They go back to faded photographs like these. For here, on a California racetrack in 1872, sequence photography was born. It started with Muybridge. Discovery begins with observation. The scientist studies forms, movement, patterns, the commonplace with the unusual. With the invention of photography, investigators saw a means of recording data from the fleeting world of events to isolate segments of time for study and analysis. It was Edward Muybridge, photographer extraordinary, who made the basic, essential contribution. Using wet plates and the cumbersome equipment of his day, Muybridge undertook studies of animal motion. At a racetrack near Palo Alto, he set 24 cameras in a row and devised an effective tripping mechanism. The result, these sequence photographs of a moving horse and rider. The science of photographic motion analysis was off to a galloping start. Muybridge's studies of human and animal motion were classics. They were soon followed by others. Thomas Edison's time-lapse photographs of 1904 used the technique in reverse. Hours were compressed into seconds to reveal the unfolding of a blossom. The growth of crystals received Edison's attention in another time-lapse sequence photographed in 1914. Today, scientists use the same technique to show the slow growth of flame crystals. The elaborate equipment of today, adapted to a variety of special purposes, finds many uses outside scientific research. From measuring the velocity of a golf swing to advertising how well a certain article of clothing will stay with the wearer. But in the design and testing of modern weapons, as in other tasks of science and engineering, photography remains of crucial importance. This test range, operated by the Naval Ordnance Laboratory at Fort Lauderdale, is lined with camera stations. The method invented by Muybridge is applied to another kind of subject, photography of missiles plunging at supersonic speeds. The pictures that result offer specific information on the missile's speed and acceleration, position and attitude during each movement of the flight. They are the evidence on which the test is evaluated. These airdrop tests are also tracked with the shoulder mount camera constructed at the laboratory. The camera follows the missile from drop to impact, revealing every detail in the sequence. These shoulder mounts, developed over a period of 20 years, illustrate one of NOL's contributions to progress in scientific photography. Photographic services at the laboratory have dimensions that Muybridge could not have foreseen. But amid the preparations for this underwater test, the purpose of one piece of equipment would be familiar. The sequence programmer is a direct descendant of the electromagnetic exposing motor that Muybridge built for his experiments. Both machines serve to synchronize the camera to the event. The high-speed cameras expose their 100-foot magazines within 1 second. The programmer times their operation to catch the missile model's brief flight. At 7,000 frames per second, multiple cameras register the model's passage in slow motion. Every frame offers significant data on the test. In the analysis of test photographs, the timing marks that stripe the edge of the film are essential. Using them, the analyst can measure velocity and acceleration because he knows the precise time difference between any frames on the roll. A pulse generator is used to mark the film while it is running through the camera. Up to 10,000 pulses per second and even higher rates can be supplied to meet any test requirements. The generator pulses this bulb to expose timing marks directly onto the film. Because NOL needs portable, rugged units, the laboratory's photographic staff has designed and constructed special timing components. They reduce the units required from an unwieldy collection of equipment to this lightweight outfit. At the NOL Open Ballistic Range, Edward Muybridge would recognize the line of camera stations. Their placement follows the technique he developed. But to photograph ballistic projectiles in flight, spark gaps are used. Flashing at 1/1,000,000th of a second, their shadowgraph pictures record the projectile's position and show shock waves and turbulence throughout the flight. At the laboratory's hyperballistic range, an 8-inch gun breech block is used to fire projectiles down this 1,000-foot tunnel past these camera stations at speeds of 15,000 feet per second. An intricate system of mirrors and spark gaps is used to produce shadowgraph pictures. In the darkroom, the developed plate shows a clear image of this nose cone configuration caught at an exposure of 1/2,000,000th of a second. Schlieren photography, another technique, reveals minute differences in atmospheric density. This system complements the shadowgraph by uncovering different aspects of the same phenomena. Its sensitivity is due to this complex optical system, employing delicate knife edges. The smallest atmospheric disturbance in the subject field is registered as a pattern of refraction on the photographic plate. At the laboratory, much research is devoted to explosive detonations. To make scientific measurements of these phenomena, another type of camera is needed. This camera incorporates a rotating mirror to achieve a rapid framing rate and exposures as brief as 1/4 of a millionth of a second. It produces valuable information on what happens at each stage of the detonation. In another type of camera, the rotating mirror is used to spread the image of the detonation along the length of the film. For this reason, it is called a streak camera. The pictures it produces look like this. But to the trained interpreter, they offer a complete record of the detonation. Recently, research workers at the laboratory succeeded in combining the advantages of the framed image with those of the streak camera by constructing a third type, a high-speed focal plane shutter framing camera. This complex instrument offers complete coverage of the event through 6 focal plane shutters, together with greater optical efficiency and shorter exposures, as brief as 1/50th of a millionth of a second. Now, let's see how some of these photographic techniques serve the investigator. This project tested the safety limits of a nuclear reactor. The scientist will have to rely on photography to chart the movement of this weighted plug. The laboratory's photographic engineers study the test specifications to outline methods of coverage and their equipment needs. They calibrate the lenses to be used for focal length and optical center. They have surveyed into position the camera stations and the stadia tower that serves as a reference point for measurements. In all, 7 cameras will observe the ejection of the plug. On a 50-foot tower are 2 35mm cameras. High-speed 16mm cameras are fixed on this 30-foot tower. The sequence programmer links all of this photographic equipment to the control room. Here, as the test begins, one button sets in motion a complex series of events. The ram that carries the explosive charge begins its journey upward. Within a few seconds, it trips a switch that turns on high-intensity lights and starts the 35mm cameras. Next, the ram locks itself, starting the 16mm cameras and detonating the explosive. The test is over, but the movement of the plug has been recorded by 7 cameras at speeds ranging from 24 to 6,000 frames per second. Meanwhile, the oscilloscope cameras have recorded the pressure time curve inside the test vessel. In this one experiment, a battery of modern photographic techniques has served the cause of investigation. Photography has become a versatile and potent instrument, aiding the scientists' powers of observation, removing the barriers of distance, controlling the swift passage of time, penetrating invisible currents of air. As for Edward Muybridge, who made the first practical application of photographic motion analysis, he did indeed prove what he set out to prove, that all 4 feet of a running horse are off the ground once during each stride. This has been a boon to artists, horse traders, and veterinarians, and photography has been solving tough problems ever since.